Ready to begin again? Okay. So what we're going to do now is we're going to go through this in Matlab. So we're going to be using the actual NIRS toolbox. We're going to be working off of the data set that's called NIRS course demo data that was on Bitbucket. So if you haven't downloaded that data set, you might want to do it now. But that's the data set we're going to be working through as we go. Yeah.
I don't have like hyperscan or connectivity. Does it also have to be in the online?
Hyperscanning and connectivity. These demo folders.
I have like some sort of.
I only need these two or these three for right now. These are all tomorrow's. So maybe when I zipped it, I didn't include those.
Okay, you should download it again.
Yeah, I'll fix. I meant to zip all of them, but the first one's is sufficient for now. Okay. Unless you downloaded that, did you download it recently?
Recently, yeah.
Okay. Okay. Well, if you download it again, it should be there. But for now, we're only on the first ones anyway, so it's kind of a moot point. Okay. So what we're going to do is we're going to go through this. I'm going to first start off kind of showing you some of the structures and how you do some of the basic commands and go through here. So first off, I guess let's take a look at the actual structure of the toolbox itself. Oops. No, I know that's not what I meant. Okay, there we go. So as I said, if you go into the toolbox folder, you have these namespace folders, the EEG, the MEG, dense time series, and this advanced folder. And if we looked in here, looked in plus NIRS, you'd see a series of other folders, which are again namespace. So like the I/O is our input/output functions. So everything that's like like the load functions and reading data, that's all going to be in here. Math, forward and inverse models, and so on. And so we'll go through some of these features. But the way that you end up calling this, say you wanted to call, again, if you look in that I/O folder, we have a function called, let's say, load NIRX as one of the files. So what you would do to call that function is you would say nirs.io dot, and then if you hit tab like this, it'll give you an option. So if you can't remember what you wanted to do, whether I used a capital N or a lowercase n in NIRX, you can go and, yeah, sorry. Okay, so if you go and you hit tab, right, it'll, if you remember, it begins with load, and then you hit tab, it'll try to fill it in with, what the available options, and you can go and select it. So if you forget what things are called or whatever, that's a really handy trick to go through this. What it's doing is it's fundamentally calling this, in this case, this load boxy function, which exists in the plus NIRS plus IO folder. Okay. So if we look again in the toolbox here, and we look in demos. So inside the demos folder, I know a lot of you guys have been going around running a lot of these. So inside the demos folder, we've put a number of these examples that are fairly well documented that run kind of, they're self-contained. So if, for example, you run the FNIRS analysis demo, what it starts off doing is it downloads data. If you already have the data, it skips the stage, but if you don't, it downloads a zip file from Bitbucket and then runs you through all the different analysis. So if you open up that file, just hit go, open out that file, change the directory in the front because you have to set it to be your computer, and then hit go. It'll just run through and actually generate all these figures and stuff like that. So all of these different examples are these different demos are all fairly self-contained in that they should just run. If you do have problems with these, please let me know. I'm trying to, we're lucky enough at here that we have every Matlab toolbox, but that means I have a tendency of using toolboxes that I didn't even know I used, and I'm trying to code it so that everyone doesn't need it's your toolbox that Matlab sells. So if you encounter a problem like that, just please let me know and I'll try to code around it. I've tried to catch most of them such that right now I think we only need the stats and the signal processing. But okay, so the various, just in here, just to show you, the code testing demo, that one goes through, and what it does is it first runs what's called a unity test, which takes a set of known answers. If I process this data, I expect the answer to be 4. And it runs through those known examples and tests whether or not that's still true. So it compares a stored solution to what it calculates at that point to make sure that the toolbox is still working in terms of Ted hasn't messed something up at 4 in the morning coding it for the NIRS course 2019. So that's the code testing demo. As it goes through that unity testing, it then goes and does shows how to do like rock curves and stuff to look at pipelines and compare results. I'm going to skip that one for a second. The FNIRS demo and FNIRS analysis demo 2. If you start with one, that's probably the one to start with, the analysis demo. So what that one does, that does the very basics of loading in data. It shows you kind of the structure of the data files. It shows you how to change stimulus names and timing, runs through the first level analysis model, and so on. So demo number 2 does the same thing, just adds a few features. I think it adds reason of interest and stuff like that, and kind of explains a little bit more. So those are probably, that one in particular is probably the one to start with. And actually, most of what I'm going to show you moving ahead here is kind of like derived from stuff that's in that one. Compare software demo. What that does is that does a that's from one of the papers that we published before, in which we have a figure that's a head-to-head comparison of Homer, NIRS, SPM, and our code. And if you run that code, it'll actually generate that same figure that's in the paper from a head-to-head comparison. So if you don't believe me that ordinary least squares is probably not the greatest idea, that will hopefully show you. Connectivity, we're going to hit this tomorrow, but that's all the resting state and the hyperscanning that shows how you use some of those tools within our code. Group analysis is kind of the stuff, again, we're going to talk about today and show you how to set that up. But this code does some rock curves in the group analysis space. To keep a little bit of backwards compatibility, we do have wrappers for Homer and NIRS, SPM, and so on. So you can actually call almost all the features. If you had your favorite motion correction wavelet-based model that Homer 2 offered as a pre-processing step, you can actually call that directly from my toolbox as a wrapper that calls where you can actually make Homer pipelines and then run them through my methods. And so that shows kind of how this demo downloads some of the old Homer data, and I think it shows how to interface with some of the Homer modules. Image reconstruction demo we're going to hit tomorrow, but that shows, so Tong's going to present that tomorrow. Guess what that does? Forward model goes through how to generate these sensitivity profiles. If I have a brain, how do I calculate the sensitivity of my probe to different regions and so on? And then registration demo talks about 3D registration of a probe to a head and different operations there. So these are all self-contained demos. If you just run them, they should work. And then in addition to that, we have a folder within there called examples. And examples are a little bit different. So a demo is completely run, self-contained. And an example is kind of a little snippet of code where someone at a conference like this asked me, how do I actually pick on Adam there? Adam one day asked me, how do I show scatter plots from my mixed effects model? And so I'm like, okay, fine, here's the demo for it. So they're fairly detailed in their naming. But it's kind of one very specific thing that we're trying to show. A lot of these don't actually come with data. They just show the lines of code that you would need to do that. So a lot of these don't actually work in terms of you hit go and it's going to complain that data not found or something like that. It wasn't intended to actually be run. It was intended to kind of show people how to do things. Okay. So in here, how to add total hemoglobin, how to calculate metabolism. I think that one's actually broken right now. Subject level stats, a little bit of EEG analysis showing how to do that. NIRS data, regions of interest, some multimodal analysis that I'm going to show a bit tomorrow. How to do deconvolution, we're going to show that today. Nonlinear GLM, these tensor-based multimodal data that I have no idea why I put that as an example, because I'm probably still about 12 months away from publishing that paper. So I probably shouldn't give people the ability to do that quite yet, and how to do things like permutation testing and bootstrapping within your data. So, okay. So that's kind of the outline of the toolbox, but what we're going to do now is, so I'm in this, so we're going to start running what is demo scripts number 1, and we'll start looking at this in terms of what the structure of the toolbox is and so on. So the only line you should need to change here is this line 27, which obviously you probably don't have a user called Upper on your computer. So you change this folder to whatever folder that demo data actually lives in. If a shortcut to that is if you just move to that folder. So if we move to that folder, and then we just type folder equals pwd. Pwd means my current folder. So I just need this folder variable to be named, where the data actually lives. Okay, so make sure that that's right. And then what we can do is let's store the output as raw and say NIRS.io. And we're going to say load directory, and we're going to give it that folder. And what you should see is it should go through, and what it does is it goes into that directory and it finds any files that it's able to read. We're going to see this in a little bit, how using this directory can help you load up multiple subjects and multiple groups and create whole hierarchies of analysis there. But in this simple example, there's only one file that existed in that folder. And so it goes and it tells you it now loaded that one file, and it returns back this structure that looks like this. So this is the structure of our data, kind of the core data time series object. Okay, so this is what we hold all the time series, the stimulus information, up until the point that we do that first level statistical model. And this as I said, this is an object. So it has certain fields associated with it. So description usually gets populated with the name of the file that it read in, although you can put anything in there, which is a comments field. The data field, this is my 1,200 time points in this data by 8 channels of data. So this is time by a number of source vectors. The probe, we're going to see that in a second, but it's actually its own object class that can draw itself and so on. So we'll see what that looks like in a second. Time is the time point, the sample point for those 1,200 time points. FM is frequency modulation, which should be 0 in all your data because it's a continuous wave system. My toolbox does support frequency domain NIRS, which is kind of more that baseline estimate stuff, in which case this would be non-zero, but for our data sets, we're still at 0. Auxiliary stimulus and demographics are all this type dictionary, which I kind of presented this morning showing you. We're going to take a look at that in a second with what's being stored within those variables. And then FS here, sample rate. This is an example. This is actually a dependent variable. So knowing the time, I can calculate the sample rate, right? So this is so if I was to change the time vector here, it would automatically refresh to change the FS. This is calculated on the fly from there. No, so if I said raw.fs equals 20, it'll complain. I don't know if I ever see that. But it says it's a dependent property that must be. So it does not allow you to change it that way. So if you get a message like that, it's because you're calling a dependent variable. Okay, so let's look at raw, and if we
if we type the command methods, what methods does in Matlab is it'll give me a list of all the functions that can be evoked on that type of object. So if we say methods of a number, like 2, which is a double, we'll come up with a whole bunch of things like you can add it, you can subtract it, you can multiply it, etc. So it's a huge list of methods. For our data here, the NIRS data core, the methods, there's basically 4 methods in it. There's data itself, which is called the constructor, which is used to create the variable in the first place. There's draw, which if we evoke that method, is going to actually make a plot and draw the data. We'll see that. Get stim matrix will actually return that design matrix, that X matrix, and it takes arguments of what kind of basis set and stuff to use. And then sorted, what sorted does is actually sorts based on channels and source detectors, so it kind of orders the data a little bit. Usually you wouldn't call that one directly. That's something that gets called behind the scenes from my end of the code. So let's take a look at what happens. So if we say raw.draw, and this should give it an argument of 1, telling it let's draw just the first channel of data. And everyone else's computer is probably going to be faster than mine because again I'm doing this screen capture thing, which I probably need to stop. Okay, this is ridiculously slow. Okay. All right, so raw.draw, you see that this was the demo data that I kind of showed in my original. This is the fictitious data that came out of the Homework 1 toolbox. But what you see here is it plotted out the time course for channel 1. It puts dim marks based on that stimulus vector, that was data, that was information that was entered in the actual NIRS file when events occurred. And you see you plotted it out like this. Okay. If we said raw, just draw by itself, it'll draw actually all 8 channels of data. So it'll look like this. You just drew all 8 channels of data like that. Okay. So, and if we look over here, okay, so I showed you what raw is. I showed you what draw means. Let's look at dictionaries. So if we look at So let's use an example. Let's create just a blank dictionary. So what we did was we evoked the dictionary command to create a blank object called D. And what this is, D is a dictionary. Oops. So if right now we see it's empty, but if I go and I assign something like gender, right? So now D is a dictionary containing the entry gender. And I can recall that back by doing something like that, and it returns F. And so you can use this as a way of storing different types of variables, much like you would a cell array. But the difference is you don't have to remember, oh, the third entry corresponded to the gender. You just type the word gender and it returns back what entry it is. So you don't have to keep track of which entry, which index was which within there. And if we look at the raw data variable, we see that demographics, stimulus, and auxiliary are all part of this dictionary class. So if we go and I'm sorry, I keep having to refresh my screen to keep it on top there. But let's look at stimulus. So we see that stimulus is a dictionary. It contains one entry called stim channel number 1. And this entry has all my stimulus events within it. Okay? So if we go and we said, let's try to capture what that looks like. And so if I said, give me stim channel 1, what's going to happen is it's going to pull that entry out of there, and this is the stim events that are storing the onset, duration, and amplitude of that timing variable. So we saw that there were 3 events. If I looked at the onset times, you would have seen the time marks. It's always in seconds relative to defined in the same space as the original data, so line with 0. duration is the duration of each of those events. And then amplitude, what amplitude is in most studies it's going to be 1, but amplitude allows us to do these parametric studies where, let's say as an example, I'm doing an experiment, a cognitive task, and the subject does it over and over again, and I record reaction time. And I want to ask the question, what part of the brain was more active for the trials that the subject was slow? And so what I would do in that case is I would create my design matrix, and I would have 2 regressors. I would have one regressor for each trial that was exactly the same amplitude, and I would have another regressor which the amplitude is varying according to the reaction time. So it was higher amplitude for higher reaction time, lower amplitude for lower. And so what I do when I put in that model is now I'm estimating, again, that idea of an intercept and a slope. The intercept is the average brain activity. The slope is how did the amplitude of the trials that had higher reaction time vary, where did the trials that had higher reaction time also have higher brain activity, right? And so you can test statistical tests on that slope curve would find this interaction between reaction time and brain activity. Okay, we're going to see that tomorrow. I'm going to show. I said I was going to do time modulation to show how to do something like that. Okay, but that's what this amplitude field gets stored as. Okay. So let's see what I wanted to show. Oh, probe. Okay. The last thing of interest, at least at this point, is this probe field. So we see that this NIRS, this probe field in the data object is what's called a NIRS core probe. It's its own type of object. And what we can do with that object, so we can say raw.probe, and if we looked at its methods, actually let's just start with there. So raw.probe, so the probe object it's a probe. It contains optodes, which is the list of source detectors as a table. It contains a link, which is the source detector pairs and which wavelength it is. So you see you have 8 entries there, and if we look at .link, if we look at that, we see it tells us the identity of each source detector. So when we plotted out that first channel of data, that represented source 1, detector 1 at 690 wavelengths, and so on. So this matches those 8 channels that are in the actual raw data file. Okay. All right. I'm not going to have to go to the gym with all the walking back and forth that I've been doing here. Okay, and so like distance. So this optodes field is sorry, you can't see. The optodes field here is this is actually what defines the entire layout of the probe. It's the sources and detectors in their XYZ position, whether or not they're a source or a detector, and then the units on XYZ, in this case in millimeters. And this table actually controls the source detector positions in terms of if I, come on, I'm really getting sick of that. So if I type source positions, right, there was one source, it was at 20, XY was 20. This is a dependent variable that was actually called in reference to that table. So when I asked for give me the list of all the sources, he went back to that table and it extracted a list of all the sources to give me those positions. So one of the as you start going through and you start trying to code, you might be tempted to try to change this field here. You have to actually change it in the table. And if you change it in the table, it'll be reflected here. Okay. Same thing with distances, that probe.distances. This is based on the source detector pairs, and it's computed on the fly based on that distance. Which also means that if you change your measurement list or you change the order of things, it automatically gets reflected here too. So everything is self-consistent. Okay. Finally, if we say we can evoke the draw command, And what that should do is that should actually draw what our probe looks like. So very simple probe, source in the middle, 4 detectors around it like that. Okay. So this is the simplest example I had. All right. So what we're going to do is you're going to suspend disbelief for a second, but I just ran the entirety of the first level analysis model in one click. And we're going to come back to exactly what was in this pipeline. But for now, let's say I created a job. That job defined a pipeline, which was my default single subject analysis. And right now it's running that analysis on this one data file. And it finished and it created the subject stats variable. All right, so that's because I want to show you what that subject stats looks like. Actually, before that, let's look at, it also created, as it was going through, it took the raw data, calculated output density, calculated hemoglobin, and we actually output this variable called HB, which you see is also a data type, just like the raw data was. If I say HB.draw, it's going to draw itself, just like the raw data did. All of the information about stimulus and auxiliaries and demographics was propagated along because it was inherited from the older, the raw data. If I look at the probe, though, and I look at the link of it, now instead of saying 698.30, it actually says opsy-deoxy. Okay, so it's kept track of what was actually done in terms of operations to the data like that. Okay? So let's look at the subject stats variable. Subject stats. So the subject stats, so we've seen so far, we've seen the data, the time course class, we've seen the probe class. Channel stats is the last kind of major class that we're talking about at least today. And channel stats is basically the variable that holds all the first and then second level statistical models. Okay? So again, we have the description propagated all the way through. So this is the same as the raw data from which it was derived. The variables, so that's a table of all of the betas and stuff like that. We're going to see that in a second with what's actually in there. And then things like beta and t-stat, p-value, q-value are all dependent variables that depend on both this table and this covariance. Okay? Same probe was propagated through demographics, the conditions that were in there, the basis set that was used in the first level model. So it's all stored within the variable, and we'll see how we can use that later on. But this is just, for now, let's say draw. And so what this is going to do, just like the raw data or the probe data, it draws itself. And so if you say stats.draw, by default, it's just going to display the student's t-test, so the t-value as a function of the different source detector pairs. It's color-coded based on the t-value. Again, this was extremely fictitious data, and actually, if you look at it, deoxy goes the wrong way because I simulated it wrong because, again, junior grad student. But right, so here you see, you got two images, oxy for stim1 and deoxy for stim1. But this is a map of the the statistical areas for that. And if you say draw, oops, if you tell it to draw with no arguments, it's going to by default, it's going to use the defaults, which is a t-score with no thresholding. But we can explicitly tell it, I want to show a t-stat, I want to scale it, I want to auto-scale it, so empty set. You could also say like, scale it between -4 and +4, or something like that if you want to apply a specific color scale. And let's say Q less than 0.1. So what this is going to do is now it's only going to show me channels, and of course everything survives. That wasn't useful. Let's do a threshold where not everything is going to survive. Okay, let's find a threshold where not everything is going to survive. Okay, so, oh boy, I have to go out to. Okay, well, you get the point. This is fictitious data. Your data doesn't normally look like that. But if you issue the command, draw, the third argument here is the threshold. So what's going to happen is it's going to draw it's going to draw all your source and vector pairs, but it's going to draw a solid thick line for anything that met that statistical threshold. And it's going to be a dotted line for everything that did. So you can identify which channels were actually statistically significant. Now there's two things that can go in here. There's P and Q. P is the kind of the raw P value. Q is the Benjihani-Hochberg false discovery corrected P value. So this is Q is far more strict. It's correcting for the fact that this probe actually has 4 source detector pairs and 2 different oxy-deoxy. So there's actually 8 comparisons that are being drawn here, and this corrects for all 8 of those comparisons. Okay? The Q value in the stats variable, and just in general, the Q value that we do, always corrects for everything that's in the structure. So if you have a stats variable that has 100 conditions and 50-some channels and oxy-deoxy and total hemoglobin and all that, it's going to be a fairly substantial correction because you have so many different comparisons in there. But if you want to say, here I'm correcting for both oxy and deoxy, and say, well, really, I didn't care about deoxy at all. Let's be a little bit less, let's be more flexible with our stats. What you can do is you can remove deoxyhemoglobin from the variable, and then now since the variable doesn't have deoxy, it only has oxy, now that Q value is only going to reflect 4 source detector pairs rather than the 8. Okay? I'm going to show later how to do that, how to remove things like that, or remove conditions. But just always be aware that your Q value is always kind of on the very conservative side. It's correcting for absolutely everything. Okay. And what you did see is you saw me issue the table command here, and the table command, it kind of gives it prints out a the estimate of the source detector, which condition it was. It gives you back the data, the standard error for that particular data, the t-score, how many degrees of freedom, which is a non-integer because I didn't talk about it in my stuff, but Tom had those equations there. Because we're doing these weighted versions, right, and we have this time course, and you were an outlier, so you went to 0, you were kind of an outlier, your weight went to, say, 0.5, like that, we end up with kind of non-integer number of samples within our data set. So hence, it's the trace of that weighting vector that comes out as the degrees of freedom here. But that's the p-value, so if I'm 10 standard deviations away, I'm significant at 10 to the 23rd, fictitious data. But then this is the Benjihani-Hochberg corrected version. And then this is the power, which is described actually in that the Toolbox paper that just came out that has all the equations for the power. But and I can never remember the equations for the power. But what it is, it's an estimate of the beta power for this first level model on a channel by channel basis. And it's estimated by basically computing what's called the minimum discoverable unit. And it's the minimum change that would be needed to exceed 0.05 and whether or not your data, the noise in your data would have let you measure that change. And there's an equation in there that's drawn from some statistical paper that's referenced in there. And I can't ever remember the actual equation. But that's the estimate of power that's estimated at the first level model. And of course, this data was such a huge change and so on, you're extremely well powered to see it because it was just so huge. Okay. All right. So that was subject stats. All right, so let's go. All right, showed that. Okay, there's also some features here. So if you say subject stats.draw is going to draw itself, but subject stats.print all, it takes the same commands, tstat, the threshold or the scaling, let's say p less than 0.05. And then what you do is you give it a folder name. We'll just use the current folder. And I want to store the data as a TIFF image. And what it's going to do, what that does is that will draw all the images, but then immediately save them in the folder I asked for, so that you have these saved like this. As soon as it goes, come on. So you actually saw that the files appeared here, and that's exactly what got drawn in that image. Okay. So that's useful if you know, you want to save the figures. You could have just launched, you know, drawn the Matlab figure and then just gone up to the file, pulled out and say save as and stuff like that. It's the exact same thing. Only when you have 20-some conditions in your file, that's a whole lot easier. So that's the print all command. We also have so there's a really useful command that I wrote here that's called it's in the NIRS utility folder. And it's called copy table to clip, which basically what it does is it takes any of those Matlab tables that I'm outputting, that stats variable, like that. And if I do that, it will copy that table to the clipboard, so I can go over to Excel and paste it back in, and I'll get that whole map of source, detector, data, standard error, power, etc., pasted into Excel. That word. I'm just talking pretty well. We also have one called Write Excel. There's another one, Read Excel. So for those of you who have Windows computers, you're lucky because Matlab works really well with Windows, Excel, and Windows. For those of you who have Macs, it doesn't work as well. It does work, but it doesn't work as well. So we actually have this is something off of Matlab Code Central that's been modified a little bit, but it's actually a really nice one that works in both Windows and Mac. And what it lets you do is actually create sheets. So what we can do is we can create these Excel files, storing that table, and then if I wanted to, I could create one sheet for every subject or something like that. And it's actually a really nice function for dealing with that, particularly if you have a Mac where you didn't have that right Excel commands. Yeah, and I think if you do this, and we'll see later on that we use the same when we start to do group level and so on, we might have 10 files, in which case at the first level we're going to have 10 statistical variables. If I feed it in here and say my Excel file and subjects, and this was an array of 10 entries, it'll actually save each one into a separate sheet automatically. So a lot of stuff works like that. It's also, let's say, so going back here, all of these variables are, you can do things like you can stack them. You know, this is just duplicating, so it's kind of, I got to learn to spell right. Right, so now, raw has 2 entries in it. I just duplicated the entries. But if we had, this is say we have 2 files, now when I run those analysis, it'll actually run it on both files like that. If I issue commands like draw, and it actually was an array, it should end up drawing plots that have both figures within there. So you end up with something like this, duplicated because it's the same file. But we've tried to be like with the stats variable and stuff. If you have 5 entries in the stats and you want to draw them, it should draw an image of all 5 of your subjects like that. Just be careful, because if you have 200 subjects, this will take forever to draw, and it'll be so small you'll never be able to see it. Okay. All right, so I showed you, I'm going to not do those quite yet. We're not ready for those. But I showed you kind of very basic command line. We loaded up some data. We looked at what it looks like in terms of the structure. What I'm